All right, today we are cracking open the rulebook for, well, for pretty much all modern electronics. We're talking about Kirchhoff's laws. And these two rules, they're like the hidden operating system behind every single device you own.
I mean, have you ever taken the back off a device, your computer, maybe even just a TV remote, and you just stare at that miniature city of circuits? It is this incredibly complex maze of paths and components and connections. Honestly, it looks like pure chaos.
So the big question is, how does anything navigate that? I mean, how does every little electron know exactly where it's supposed to go? Well, it turns out that underneath all of that complexity is this beautifully simple order. And it's all governed by just two rules written down, get this, all the way back in 1845.
So these rules are basically the essential roadmap for every circuit out there. Let's meet the man who first drew that map for us, Gustav Kirchhoff.
Yep, that's him, the German physicist Gustav Kirchhoff. Back in 1845, he came up with two laws that just completely revolutionized how we understand electrical circuits. I mean, this laid the groundwork for literally everything that came after. Okay, so what are they really? Put simply, Kirchhoff's laws are a set of two rules. They tell us exactly how current, and you can just think of current as the amount of electricity flowing, how it moves through a circuit. And they also tell us how voltage, which is kind of like the electrical pressure pushing it all along, how that behaves in a closed loop. These two things are the essential tools for taking apart any circuit. I don't care how complex it is.
All right, let's start with the first one. This is called the junction rule, and it's all about, well, junctions, or nodes in a circuit. You can really think of it as the intersection rule for electricity, and it's all based on one super simple idea. What flows in must flow out.
And the best way to think about this is with water pipes. Seriously, imagine a bunch of pipes all meeting at one single connection point. You can't have more water flowing into that junction than is flowing out of it, right? I mean, where would the extra water go? It's impossible. Well, electricity works exactly the same way. And that simple idea leads us right to the formal rule. We call it Kirchhoff's current law, or KCL for short. It just states that the total amount of electrical current going into any point in a circuit has to be exactly equal to the total current coming out of that same point. It's a perfect balance. Not a single electron gets lost.
You know, this isn't just some handy rule for circuits. It's way bigger than that. It's actually based on one of the most fundamental principles in all of physics, the conservation of charge. The idea is simple. You can't just create or destroy charge at an intersection. It has to go somewhere. It has to keep moving.
Okay, so that's KCL. It covers what happens at a single point. But what about the journey around a whole circuit? For that, we need the second law. This is the loop rule, and I love this subtitle for it, the round-trip journey rule.
Here's another great analogy. Imagine you're going for a hike on a trail that's a big loop. It starts and ends at the exact same spot. Now, along the way, you might climb up some really steep hills, go down into some deep valleys. But when you finally get back to your car, your net change in elevation is zero, right? You're right back where you started.
Well, that is exactly what Kirchhoff voltage law, or KVL, is all about. In a circuit, voltage is like that elevation. As you travel around any closed loop, the voltage is going to rise, say when you go across a battery, and it's going to drop when you go through components, like resistors. But by the time you make the full loop and get back to where you started, the sum of all those gains and losses, it's exactly zero, every single time.
And yep, just like the first law, this one is tied to another massive fundamental concept in physics, the conservation of energy. You just can't get more energy out of a circuit loop than you put into it. It's that simple. The books have to balance.
So there you have it, two laws, one for junctions and one for loops. And when you put them together, they give you a complete picture of what's happening in any circuit.
So let's just break that down side by side. You've got KCL, the junction rule. That's all about current, and it happens at a single point, a node. And it's based on the conservation of charge. Then you have KVL, the loop rule. That's all about voltage, and it happens over a whole closed path, a loop, and that's based on the conservation of energy. I love this way of thinking about it. One is a snapshot of a single point, and the other is the story of a complete journey.
Okay, so why should we care about a couple of rules from the 1840s? I mean, really? Well, because these rules are absolutely everywhere. They are the foundation underpinning all of our modern technology.
For any electrical engineer or physicist, these laws are the essential toolkit. With them, you can take any circuit, I don't care how tangled and confusing it looks, and you can figure out everything. You can find unknown currents, hidden voltages. You can even figure out which direction the electricity is flowing in different parts of the circuit. It's no exaggeration to say this is the absolute bedrock of all modern circuit analysis.
But like pretty much any rule in physics, it's really important to know where the boundaries are. Even laws as fundamental as these have their limits.
So here's the fine print, if you will. Kirchhoff's laws work perfectly, but they have one key assumption, that there isn't a fluctuating magnetic field nearby. Because if you have a strong changing magnetic field, that field can actually create or induce its own currents and voltages. And that, well, that can throw the whole calculation off. So the laws are perfect for a specific self-contained circuit, but they can get a little less precise in more complex electromagnetic environments.
But let's be really clear here. We're talking about edge cases. For over 175 years, these two simple, elegant laws have been the unshakable foundation of electrical engineering. We're talking from the very first telegraphs all the way to the supercomputer that's probably sitting in your pocket right now.
And that really brings us to a final thought, doesn't it? If a pair of laws discovered more than 175 years ago still forms the bedrock of our entire digital world, it just makes you wonder, right? What other simple, fundamental rule about our universe is just sitting out there, waiting to be discovered next? What's going to be the next Kirchhoff's law?